Hello, class. Welcome to another episode of System Introductions to System Programming. Learning outcomes or objective. At the end of this class, students should be able to explain the general format of an assembly language. What is an assembly language? An assembly language is a low-level programming language that is easier to read than machine language. It uses symbols and shortcodes known as mnemonics instead of binary numbers. And it is worthy of note that each CPU has its assembly language. So it allows the direct control of computer hardware. And this assembly language is used to write operating systems, device drivers, and other operating system programs. I think we've discussed this in our first week or thereabout, where we discussed about assembly language. We talked about translation, where we talk about instructions are translated from high-level language to assembly language to intermediate representation down to machine language. These are stages in which these particular programs are translated into. So, in this class, we will be looking at this assembly language in details. Now that we know what an assembly language is, what it is made of, let's now look at the structure of an assembly language. But before we look at the structure, let's now look at how the naming convention in assembly language. First, the labels. To name any label in an assembly language, you start with a letter, and it should start with a letter and include combination of letters, numbers, and underscore. Example: loop underscore start. If you look at that, loop underscore start is an example of a label in an assembly language. As stated, it must start with a letter or which can include combination of other letters, numbers, and underscore. So if you look at loop, L-O-O-P underscore S-T-R-A-T, start. So it conforms with the initially stated rule. 2. Mnemonics. It contains short code for instructions. Example: move, add. Move simply means move a particular component or to a memory location. Add sums two numbers. So if you can see, it can easily be understood by humans because they are closely related to our normal English language. 3. Registers. Short names based on the CPU type. Example: AX, BX. All these are memory locations and they are type of what? Registers. Subsequently, we'll discuss extensively on registers, but just know that registers are memory locations in an assembly language. 2. Constants. We use uppercase letters and underscore. Example: max underscore value. So you can see max is talking about maximum underscore value. So this is a naming convention. It also satisfies the first naming convention, which states that start with a letter and can include other letters, numbers, and underscore. Last but not the least, variables. We use descriptive names, often lowercase or mixed case. Example: counter, temp underscore value. So if you look at this, we're just trying to come up to inform you about the rules of naming in assembly language. The next thing is we will look at statement in assembly language. And we know that a statement is a single line of code or an instruction that performs a specific action. So an assembly language program typically follows this general format. As stated earlier, look at the label, a symbolic name for a memory location or instruction. It's placed at the beginning of the line, followed by a column. Example, say loop, then column. So this indicates that this is a label. Immediately you see a name followed by a column in an assembly language, know that this is a label. Now, mnemonics representation. These mnemonics represent the operations or instructions to be performed, e.g. move, add, sub, div, mul. All these are operations or the instructions that need to be performed. So it is predefined keyword that specifies the operations. I think before in the previous slide, I've explained this. Move is to what? Move a particular item to a memory location. Well, add some two numbers, subtract to what? Performs a difference operation between two variables. So operands, which are optional, you know them already. Normal operands is the plus for plus sign, specify the data to be used in the operations, and so on and so forth. So It can also include registers, constants, or memory locations. I believe we discussed this already. I said we're going to discuss on registers. And constants as what variables whose values, once declared, cannot be changed, or it remains constant throughout the lifetime of that program or during program executions. And memory locations are spaces where we move in variables or information for storage or in order to use them for future reference. So if you look at the example we have, this is just a short code where we say ax comma bx. When we say move ax comma bx, where ax are bx and this is what we are saying is move the contents of ax into of bx into ax. So and both of them are registers, and these registers are called 16-bit registers. So you can see, like I stated earlier, move is used to move the content of one memory variable to another memory location. So both ax and bx are registers. So if you say move ax, meaning move the content of bx into ax, meaning the content of bx here should be the content of bx here should be moved into ax. So that's just a simple example. As we move forward, we'll be looking at more and more of it. So now, these registers that we'll be discussing, what is this register? In our next slide, we'll discuss the meaning of these registers. So a register is a small fast storage location within the CPU, which is central processing unit. So it holds data that is being what? Processed or is currently in execution by the CPU. So these registers are used for temporary storage of values, such as data, addresses, or control information. So they play a crucial role in execution of instructions within the CPU. So now that we've seen the meaning of a register, we know it is small and the fastest storage location within the computer, which is the CPU, which is the central processing unit. And it holds data that is being processed. So meaning data that are resident in registers are currently being processed. They are particular data that the computer is used or is currently in use for program execution. Now, these are the characteristics of registers. One is speed. Registers are much more faster than RAM and other forms of memory as they are located directly within the CPU. So the advantage of a register is it is within the CPU, unlike RAM that is installed, which it comes in as an external memory. It can be internal because it's placed within the inside the computer physical wise, but this particular register exists within the motherboard, the central board of the computer. So that makes it faster than the RAM. Two, temporary storage. So registers can be used to hold data temporarily while the CPU is performing operations on it, such as calculations or memory addresses or manipulations. We've explained this before. We said it's used to hold data in execution. This is what it simply means. And size. So, registers are typically within between 8 to 64 bits. You see, they are small, and they have the advantage of being small. That makes them faster. Another thing is that they have special rules and other characteristics. So different types of registers are used for specific tasks, such as storing the current instruction, holding the result, calculation, and so on, or pointing to another memory addresses. All these are the characteristics of a good register. So the next, we are going to be looking at the types of registers. So here are some of the types of registers. We have the general purpose registers, segment registers, index registers, pointers registers, instruction pointer register, and flags register. Now, let's look at them individually. General purpose registers are used for arithmetic operations, data manipulation, and temporary storage. For example, the AX, BS, CX, DX are in x86 architecture are used for all these operations. You can use them for arithmetic operations, data manipulation, as well as temporary storage. Well, segment registers hold the addresses of different segments in a memory, such as code, data, and stack segment. Examples are CS, code segment, DS, data segment, and SS, which is stack segment. The next example is index registers. These index registers are used for indexing addresses and looping operations, branching, when you are branching within a code, branching within a code, yes, where these particular registers are used to point at to a particular segment of a group, a function or subroutine, as other people see it. Nowadays, these are regarded as methods. So the pointer register stores addresses that point to a location in the memory. So this is seamless. It's just a pointer, a director. It points to a memory location where it shows a point or direct to a location in the memory. Example include the SP stack pointer, BP base pointer. Instruction pointer, this holds the address of the next instruction to be executed. You can have a bunch of instructions or group of instructions. The responsibility of instruction pointer is to point at which instruction is going to be executed next by the processor or CPU. Of course, the example one, we have IP or EIP, which is called extended instruction pointer. The last but not least we call is flags register. This register contains individual flags that represent the outcome of operation or the state of the CPU. An example is the flag register, which includes flags like ZF, zero flag, and CF, and carry flags. So these are the types of registers. We've seen them individually as well as their own examples. Now, let's look at an example that shows these things in action. Now, example one. When you look at this short code, loop, move AX, BX, meaning move the content of BX into AX. So in this example, the loop, is a label. We've done an example on it already. While the move is a mnemonic, which represents an operation, while the operands are the AX and BX, which represent memory location where data are stored. So this comment is just talking about move the content. The move the content is just a comment representing, is a comment explaining the movement of the content of BX into AX. Another example, example 2. This particular example does the operation add two particular numbers. Now, first, we declare the numbers num1, which is the first number, num1, which is first number, which equals to 5, num2, which is second number, which is 10. Now, the result. To store the result now, we know the result is 0. So what we did was we moved num1 into AL, which is another register, which is a registrar. So we now to add them, to add the two numbers, we now add the second number into AL, because for you to perform the operation, those two numbers must exist within that location. So that is how it is done in assembly language. So add the second number to the value in AL. Now we now move the results, AL into result, to store the result in the result variable. So now let me make an explanation of what actually happened here. What actually happened here is we're trying to add two numbers, num1 and num2. So the DB5 is talking about num1. DB is just a convention or a syntax within an assembly language. There are different varieties of assembly languages. There's one of x86 architecture and so on and so forth. So what we're doing here is num1, we move 5 equals is not in num1, 10, which is representative of num2. So now to sum the two of them, first, we must have a variable that will store the two values. Because when an operation occurs between two variables, there must be a third variable that store the result of that particular operation. So the result is the third variable that combines the two results, which is 5 and 10. And another will say num1 and num2. So to perform this operation, we now declare this result, which is equals 0. Of course, it's 0 because it has no content yet. So the next thing is we move num1 into AL. AL is a registrar. So we move num1 into there, meaning the content of num1 should be moved into AL. Now, having moved it, the next thing is for us to add the second number, we now move the content of num2 in the same AL because num1 is there, and the essence of our operation is to add the two. So by the time we move num2 into there, the two numbers will be added, which is num1 and num2. So now that we move it into 2, the next thing is to store the result. Now we now move AL into what? Result. Because AL now, for you to perform any operation in assembly language, the operations will happen within register. At least we've looked at it from the naming convention. So we now move now. First we'll move the 5. Second we'll move the 10. So 5 plus 10 will give you 15. So now that 15 will now be moved into result. So at this level, instead of moving num1, num2, we're moving the AL because the two numbers are already added into a register, AL. So AL will now be moved into result, showing that what? We've successfully added two numbers and the result is stored in result. So this is all about discussing the structure of an assembly language. And the essence at this level of the course is for you to understand the structure of how an assembly language operates. So we've looked at the naming convention, we've looked at the what a register is, we've also looked at the characteristic of a register. We'll now move ahead to look at the type of registers, and we'll now discuss two examples in machine, in assembly language rather, where now we'll now explain what happens step by step at each stage. So the next thing is the quiz. This now brings us to the end of the class. The next thing is the quiz. Look at this quiz, try and brainstorm and see what you've learned so far within the class. So if there are further questions, you know what to do, place them, and in our next class we shall treat them. In the absence of any other observation, thank you. See you in the next class.